Yeah. Okay, so our speaker today is Thaísa Tamusiunas, and the title you can see there is Galois theory and then inverse semigroup actions. Please, Thaísa, go ahead.
Okay, thank you. I'd like to thank the organizer for the invitation. And so let's talk about Galois theory concerning inverse semigroup actions. Well, I organized the presentation first speaking quickly about partial objections, just as motivation. Then I will talk about the ESM theorem, and I thought this is relevant because we use this theorem here in Galois theory for orthogonal actions. Then I will talk about actions of inverse semigroups and groupoids on rings. And finally, I will spend a little more time discussing Galois theory in this context. So let's start with the partial objections as a motivation. Let X be an unempty set. Here we have the collection of all partial objections of this set. And there are two ways that we can look at this collection. One way is look with an inverse semigroup structure, and then it forms an inverse semigroup called symmetric inverse semigroup. Actually, it's the inverse monoid because it has an identity. The multiplication rule in this case is given by a composition where it makes sense, in the sense that it occurs in the largest domain when it makes sense. In cases where the domain and the range of the maps have empty intersection, then we call this composition as an empty function. For any subset, we have the identity map of this subset, and for sure this is also a partial objection called partial identity. And the empty function is also partial objection by vacuity. And then there is another way to look at this collection of partial objections by defining a different composition. And with this different composition, we have a groupoid structure. Then the composition is given by the restrictive product, and we denote it by F dot G. This product is defined only when the domain of F is equal to the range of G. And in this case, F dot G is the composition, and otherwise it's not defined. And when considered with respect to this product, then the collection of partial objections has an algebraic structure known as groupoid. In addition to the restrictive product of partial objections, we can include a partial order. So if F and G are two partial objections from X to Y, such that the domain of F is in the domain of G, and when we look at G restricted to the domain of F, they are the same, they are equal, then we write that F is less or equal to G. And then we also say that F is a restriction of G. So while Wagner and Preston found axioms satisfied by the inverse semigroup with the composition in the mid of the 50s, Edison found axioms satisfied by the structure of a groupoid, ordered groupoid, because we have a partial order, in the mid of 50s and 60s. And these two approaches have a connection. This connection is established by the Edison-Scheiner-Bulipa theorem, or simply the ESM theorem. And I will now discuss the elements of this theorem because we will use it in Galois theory in a few moments. First of all, what is an ordered groupoid? Well, before we have to know what is a groupoid. A groupoid for us is a small category in which every morphism is an isomorphism. We denote by G0 the set of objects of G, and we will consider this set in the set of morphism by identifying with this natural map. And given an element G in G, a morphism, the domain and the range of G will be denoted by DG and RG respectively. We will use this notation for the pairs that are composable in the sense that the product GH is defined. And now we can define what is an ordered groupoid. If G is a groupoid, it's said to be ordered if there is a partial order in G such that the following conditions are satisfied. So this partial order preserves inverse in the sense that X is less or equal than Y, then the inverse of X is less or equal than the inverse of Y. And this partial order preserves products where it makes sense. Then if X is less or equal than Y and U is less or equal than V, when the product is defined, we have that XU is less or equal than YV. The third condition said that given any element X in G and any identity E, such that this identity E is less or equal than domain of X, there is a unique element, this is a restriction domain, such that this restriction domain is less or equal than X, and the domain of this element, this morphism, is precisely E. And the condition OG3 star is equivalent to 3, but here we are considering the range. So given X an element in G and E an identity or an object, then E less or equal than the range of X, there is a unique element, this is a restriction range, that satisfies this restriction range is less or equal than X, and the range of this element is E.
Excuse me, may I ask a question?
Yes, for sure.
In the two versions of 3, isn't this X/E obliged to be X times E and the other one E times X, or not?
I don't understand.
Yeah, so I mean, this
element, are you talking
this
about
one is like X restricted to E, right?
Okay. X
And
restricted to
don't
E
you get
is
that if you multiply X by E?
this is you have the
No, but this is because it's a
you are
groupoid.
restricting.
Yeah,
you
it's
have
not defined.
X has a bigger domain, so we're restricting to something that is smaller.
Yeah. So you cannot interpret this in terms of the product because it's a group. The product is only defined when the domain and the range exactly match. Yeah.
Yes.
Okay.
Then using the first condition, we can prove that they are equivalent, 3 and 3 star. Okay. Now we are going to include a totally defined operation on an inductive groupoid, but I will define what means an inductive groupoid in a few moments. First, in a partial ordered set P, we say that Z in P is the meet between X and Y if, first of all, this element is less or equal than X and then Y. And if there is another element in P such that this element is also less or equal than X and Y, then this element must be less or equal than Z. And we use this notation for the meet. A post set or a partial ordered set where every pair of elements has a meet is called a meet similarity. If G is such that G0 is a meet similarity with respect to the partial order, then here we are consider G an ordered groupoid. We say that G is inductive groupoid. Given an inductive groupoid, which means that it is an ordered groupoid and also has the property of G0 being a meet similarity, we define the pseudo product star. So X star Y is equal to the domain restriction multiplied by the range restriction. Here, this product in the groupoid is always defined because this element E is the meet between the domain of X and the range of Y. And once that G is inductive, given any two identities, this meet always exists. So, and the domain of this element is E, and the range of the second element is E, so this product is defined. So, in this case, the product star is totally defined for any two elements of the groupoid. And a functor P from G to H between inductive groupoids is called an inductive functor if it preserves orders and meets. Now, including a partial order on an inverse semigroup. Let S be an arbitrary inverse semigroup. We define in S a partial operation, named restricted product, defined in the following way. So we say that S dot T is defined if and only if the inverse of S multiplied by S is equal to T inverse. And in this case, the product restricted is equal just to ST. Otherwise, it's not defined. An element in the inverse semigroup is called idempotent if F operated with F, it's equal to F, or F squared is F. And the set of idempotents of the inverse semigroup S is denoted by ES. Now we define the following partial order on S. We say that S is less or equal than T if and only if there exists an idempotent F such that S is equal to T multiplied by this idempotent. And this partial order is called the natural partial order on the inverse semigroup S. A function theta is called a morphism between inverse semigroups if it preserves the product, and it's called a premorphism if the theta st is an extension of theta s theta t. An extension, I mean, the right side is bigger. I don't know if what is the question.
May I ask you something else?
Yes.
Yeah, so do you assume that your inverse semigroups have a zero element? like the I of X?
Okay. At first moment, we will consider an arbitrary inverse semigroup, but then I will distinguish the case with 0 and the case without 0. But now I'm not making any restriction concerning the 0. So relating the categories of inverse semigroups and the category of inductive groupoids. So this is the notation that I will use for the category of inverse semigroups and polymorphisms, and this is the notation for the category of inductive groupoids and ordered functors. We consider the functor G from the inverse semigroup to inductive groupoids, and each inverse semigroup is associated to this structure that it is inductive groupoid. For sure, it is demonstrated that this is an inductive groupoid. And the functor associated here is an ordered functor. And on the other hand, consider the functor S from the inductive groupoids to the inverse semigroup. We take an inductive groupoid G, and we associate it to G star, which is the pseudo product, which is a totally defined operation, and it gives to G and a structure of inverse semigroup. And the functor is a primorphism, and it's demonstrated that. And each morphism is a particular case of a primorphism. So these functors, G and S, yield the ESN theorem that I state now. Here is the Erzman-Shainaburi-Pa theorem. The category of inverse semigroups and polymorphisms is isomorphic to the category of inductive groupoids and ordered functors. And the category of inverse semigroups and morphisms is isomorphic to the category of inductive groupoids and inductive functors. And this relation went to take an inverse semigroup and associate the groupoid, ordered groupoid, inductive groupoid, and vice versa. So we can go to any direction using the ESN theorem. Okay, let's talk about actions of inverse semigroups. Let A be a ring. We denote by IA. Here is the set of partial isomorphism between ideals of the ring A, and it's clearly inverse monoid with decomposition, previously defined. And an action of the inverse semigroup S on a ring A is a morphism of inverse semigroups beta from S to this set of partial isomorphisms between ideals of A. For convenience, I will use another notation, but it's the same, it's equivalent. So just for convenience, we will denote beta S by beta applied on S. The domain of beta S, we will use the notation A S inverse. And the range of beta S, we will use the notation AS. Then we can also define an action of the inverse semigroup on the ring A as a collection of ideals and isomorphisms before these ideals, such that this composition, this equality is true, it's valid, where the element A is in the appropriate domain for the composition, And if S is unitary with identity 1S, then the ideal indexed by 1S is the whole ring. And a unital action of the inverse semigroup S on A is defined as a morphism from S to this set, IUA, where the set is the inverse semigroup of isomorphisms between unital ideals. And unital ideals, I mean that here the ideals are generated by central idempotents. So this is what we mean by unital action.
Sorry, central importance, you mean are central in the whole of A or central in the domain?
Central idempotent generated by central and idempotent
Central
elements.
in A, in the whole of A.
In A. Given a groupoid G, this beta set to be an action. Here is a collection of ideals and isomorphism between these ideals, where AG is equal to RG, the range of G. They are both ideals of A, and each beta G is an isomorphism of rings between these ideals. And the identity maps on the identity of these ideals. And this composition applied on I is the product of GH, where it makes sense. I mean, where this product is defined and the element A is in the appropriate domain. So this is a action of a groupoid on a ring. If, in addition, G is an ordered groupoid, we say that beta is an ordered action if G less or equal than H implies that the ideal AG is in the ideal AH, and beta G is equal to beta H restrict to the domain of beta G. And if G is ordered, but it is also inductive, an inductive action is an ordered action of an inductive groupoid such that the ideal indexed by the meet between E and F is precisely the ideal indexed by E intersection with the ideal indexed by F. And here is a first
I have a
idea.
question.
Yes.
Can you interpret these actions as some functor from a bicategory of groupoids or inverse semigroups to the bicategory of rings?
Okay. An action has a functor from I can interpret the action of a groupoid has a functor from the category of groupoid to another category of groupoid. In the sense that the collection of beta G, it forms a groupoid, but maybe using the ESN, we can put another arrow and think of in a functor between the category of groupoids and the category of inverse semigroups, I believe. But I'm not considering this here, but I believe that that works.
Okay, thanks.
Okay, a first idea for Galois theory, where there is a paper that I worked with Professor Pax from Porto Alegre, Brazil, and which we developed the Galois theory for non-ordered groupoids. And the the main idea of this work between me and Pax was the work developed by Chase, Harrison, and Rosenberg when they have groups acting on commutative rings. And then the initial idea was groups acting on commutative rings. In this work, we have groupoids acting on commutative rings, but non-ordered groupoids. So I have a PhD student, the name of him is Wesley Lotchenlegger. I proposed to him to take this work and first include an order, and then to develop a Galois theory for ordered groupoids, and then translate to inverse semigroups using the ESM theorem. This was the first idea, to develop a Galois theory for inverse semigroups. However, there is an issue that must be considered. The Galois theory for groupoids was developed for actions that satisfy a specific condition called orthogonality. What is this condition? I will show. So translating this condition from the groupoids to inverse semigroups. Let S be an inverse semigroup acting on a ring A via an action beta. And this is the notation for the natural partial order of S. If the ring A has this decomposition, here we assuming that the ideal, the ring A is a direct sum of the ideals. These ideals are indexed by the maximal elements idempotents. When I mean maximal is relating to the natural partial order of the inverse semigroup. So if this decomposition is true, then we said that beta is an orthogonal inverse semigroup action. And this is a little bit restricted, but I will talk about this in a few moments. For orthogonal groupoid actions, the condition E is in maximal of ES is equivalent to E is in G0, the set of identities, because in groupoids, the natural partial order is the quality, and the idempotents are precisely the identities. So it's just the difference when considering groupoids. In particular, every group action is an orthogonal group action, because in this case, A is equal to A1, where 1 is the identity of the group. I will introduce some concepts regarding Galois theory, and then I will return to the orthogonality. So let's talk about some relevant concepts. The first one is the subring of invariants. Given a finite inverse semigroup, now I'm assuming that the inverse semigroup is finite because we are working with a finite Galois theory. And we are also assuming that this action is unitary. Then we set this subring A beta has the elements of the ring A such that these elements are fixed in the sense that beta S applied on A. This is the 1S minus 1 is the idempotent that generates the ideal indexed by S minus 1. And when we apply beta S on this element, it is A multiplied by 1S. And 1S is the ideal, not this is the idempotent that generated the ideal indexed by S. And this has a structure of subring and is called the subring of invariance. The second relevant concept is concerning separability. So given a ring extension AB, A is said to be B separable if there exists an element E in this tensor such that the sum of xi, yi is equal to the, here we are considering unitary rings. I did not mention it, but the rings are unitary. And this element commutes with any element of the ring A. This element A is called idempotent of separability of A over the subring of invariance. And when B is commutative, then it's equivalent to say that the ring A is projective modulo over this tensor when A up is the opposite algebra of A.
Wait a second. Shouldn't it be in the definition? Shouldn't it be B instead of A of the invariants? Because there is no action here, right? It's just a ring extension.
A ring extension.
I mean, there is no groupoid or no semigroup or anything. So
No, it's not. It's the same definition. Here we are talking just about separability of rings, and
Yeah.
we're not.
Yeah. So the in the
Okay. Is
it's
it?
should be B.
It's wrong here. It's B. It's B because, well, it's copy and paste. Here should be B.
Okay.
After the separability will be over the invariance, but here's the general definition, and it's for sure over B. Thank you. And now we have the definition of Galois extension. So let S be a finite inverse semigroup acting on a ring A via an unitary action. And we say that is a beta Galois extension of A beta if there exist elements X, Y, and YI such that this equality holds. And in this case, we say that this elements forms a Galois coordinate system. Here we are saying that when S is an idempotent, on the right side we have one E, that is a non-zero idempotent. And when S is not an idempotent, then the sum is zero.
Sorry, are we to think that, I mean, Galois should imply separable, right? And the X, Y, and the YI are the coordinates of the separability idempotent. In the end.
Oh, okay. In Galois theory, it's expected that each Galois extension is a separable extension. But it's something that we have to prove. And the point is that this Galois system, at the first look, they don't need to commute. When we consider the tensor, we don't have to commute. We have just, it's very similar, it's closer to the definition of separability, but it's not equal. And there is a problem when we can show this equivalence. In the case of inverse semigroups, Galois extension is equivalent to separability, that is separable, and another extra condition, which I will speak in a few moments. And then we can prove that in fact there is an equivalence. Here I included the definition of Galois extension for inductive groupoids, but it's the same. Just here we have the set of identities of the groupoid instead of the set of idempotents of the inverse semigroup. But essentially, it's the same definition. And an interesting fact is that the functors S and G of the ESN theorem induce a one-to-one correspondence between Galois extensions of inverse semigroups and Galois extensions of inductive groupoids. And with this information, we can translate the Galois theory for ordered groupoids to inverse semigroups. And the extra condition that I said before is called beta strong. Let B be an A beta subalgebra of A. We say that B is beta strong if for all S and T elements in S, such that this product is not in SB. Well, we mean that the actions are not equal. When considering S and T, beta S is not equal to beta T. In this context, if they are not equal, then the actions are strongly distinct. They are not only distinct, they are strongly distinct in the sense that they are distinct, but when we multiply with a non-zero idempotent, they remains distinct. And this condition we called beta strong. And another two properties that are relevant to say is that an inverse semigroup is called full if the set of the idempotents are equal to the whole set of idempotents of S. And an ordered groupoid set maximal if this subset is a subgroupoid. It's not always a subgroupoid. When it is a subgroupoid, we said that the G is maximal. So here is the first Galois correspondence for orthogonal actions. We have beta and orthogonal action of the inverse semigroup. A finite I did not wrote, but is a finite inverse semigroup on the commutative ring A. And suppose that A is beta Galois extension of A beta, with assuming these ideals are not zero for all S maximal with respect to the natural partial order. And then we have a correspondence that is bijective between some inverse semigroups and some subalgebras. And here we are considering on the right side, on the left side, here we have inverse subsemigroups T that are full, and also such that the functor G applied on T is a maximal groupoid considering the associated inductive groupoid. And in the right side of the correspondence, we have some subalgebras that satisfies. They are beta strong and a beta separable, such that the functor applied on this is a subgroup, subsemigroup, inverse subsemigroup, and it is maximal concerning the associated groupoid. Then in this correspondence, there are not all inverse semigroups. and not all subalgebras. There are some of inverse subsemigroups and some of subalgebras. And they are in relation with the maximality. Well, beta strong and A beta separable is equivalent to Galois. So here, these two conditions together, it's proven, and we can prove that this is equivalent to Galois. So here we are taking substations that are Galois. But the point is, this is not the best correspondence. And the reason is because the orthogonality. But this result that I put here is in this reference. Then Lachenlager is my PhD student. He did this theorem, and we published these results here in this reference. And the condition of the orthogonality is necessary to ensure the invariance of the trace map, which is a fundamental map in Galois theory. It's the trace map that allows us to construct equivalences of the definition of Galois theory, and then to work with Galois theory. So this is not the best as possible, because here we have the decomposition of the orthogonal actions. Look at this decomposition. If we have E and F, both maximal idempotents in the set of idempotents, here we are considering that each inverse semigroup has an inductive groupoid associated, and this equality holds. The ideal indexed by the mid is the intersection between AE and AF. So if we're assuming that we have a direct sum, or this ideal is 0, or these elements are equal. But if all the maximal idempotents are equal, well, then we have an inverse monoid. There's only one maximal, and then it's a monoid. Otherwise, if we have another element which is idempotent, it's not maximal, then it is less or equal than E and F, and then it's less or equal than the mid. And then it implies that this ideal is equal to 0. There is many of the ideals needs to be 0 if we are assuming this orthogonality. And by this reason, the class of actions considered is not the best as possible. And that's why in the correspondence appear inverse semigroups and subalgebras that have some maximality associated, because many people was to 0 here. And okay, so we thought, how to improve the theory? And the problem was to work with the trace map. Here I will talk about the trace map and what is the problem and how we solve the problem. We are still in the context that S is a finite inverse semigroup and beta is an action of the inverse semigroup on a ring A. And the trace maps defined has the map which for each element A, we have the sum of all elements in S of beta S applied on A1 S minus 1. This is the trace map. When S is in particular a group, It is to see that this trace map is invariant. But this shall not occur for actions of inverse semigroups. This map is not necessarily invariant. I put an example here, but I will quickly talk about. Here we are considering an inverse monoid, and we have these elements and relations, and the ring here is the ring generated by these central idempotents pairwise orthogonal, and such that the sum of these elements is equal to the identity of the ring A. Here we are defining the ideals and the actions, and we can calculate what is the subring of invariance. This is the subring of invariance here. And however, if we consider this particular element, for instance, E, the imaginary number multiplied by this idempotent, the trace map applied on this element is itself equal. But this element is not in the subring of invariance. And well, the trace map is not necessarily invariant. And it's a problem because we needed the invariance of the trace map to develop Galois theory. So the solution that we found is to work with partial actions of groups. We associate actions of inverse semigroups to partial actions of groups. And to this end, I will present here the definition of partial actions of groups, and next I will present the definition of Galois extension in this context. So now consider G a group, and A is a ring. A partial action of G on A is a collection of ideals and isomorphism for these ideals, such that the ideal indexed by the identity of the group is the whole ring, and this element identity is associated to the identity of the ring A. The second condition is associated to the third, because if we look at the left side of the equality of the third condition, here we have a composition of partial projections. And we are defining this composition in the largest domain when it makes sense. So that's why we are considering this set.
Sorry, may I ask you something?
Yes.
Isn't this, I mean, if I consider G as a inverse semigroup with unit, wouldn't this be also an orthogonal action? Because if I understood correctly, for inverse semigroups with unit, with inverse monoids, the orthogonality is simply that A1 is the whole of A, isn't it?
Yes. Oh, I don't know what is the question?
Well, I'm asking whether if I take the definition of orthogonal action of an inverse semigroup on an algebra, on a ring, right? And
Right.
yeah, and now I let the semigroup be a ring, a group.
Okay. Okay.
Then-
I understand. Here you are talking about this intersection here.
Because the
consider
P1
the
is the orthogonality condition, right?
You're
Because
talking
there's
about
only one
condition.
maximal element.
Yeah, this okay. considering the orthogonality, we have the maximal ideals, but inside each ideal, we have many other ideals. And these smaller ideals may have intersection. In the orthogonality, when we have at least two maximal idempotents,
Yeah, but
then they are all zero.
yeah,
So
but here you don't
that's
have
why
that problem
the
because there is
condition-
only one
the
maximum.
condition is weak. The condition is weak. It's not good. The condition works if we have a monoid, but otherwise the condition is not good. They are zero.
No, of course, but since G is a group, it's a monoid, right?
Okay.
You apply the
For
same
monoid,
definition as
that's
before for the
okay.
group. For a
For
group,
monoids, there is not a problem because here the only condition is that A is equal to A1. A1 is
so what I'm saying is that if you ask that S be a group, so it's a monoid,
yes.
then what I'm asking is what is the difference between asking for a group, right? You have a group, and then you say you have an action of the group on a ring, and you ask that the action be, you may ask, because the group is a semigroup, that the action be orthogonal, right? That gives you one definition. And then now you go to the definition of partial action, and if you consider the group as an inverse semigroup, then isn't that the same as the definition of orthogonal action? That's my question.
Okay, it's the same definition, but here we are not assuming anymore the orthogonality because the point to use partial actions of group is to define another trace map. And with this another trace map, we did not ask the orthogonality. The orthogonality was used to ensure the invariance of the trace map before. Now we are going to introduce a new trace map that is invariant, and we don't need the orthogonality to show it. So in this new context, we are not assuming any restriction on the action. And how we are going to construct this new trace map, it's using partial actions of groups. But here, in this context of partial actions of group, we're not working with the orthogonality anymore. So here, just to conclude here, this condition, the second condition, look that in the left side, we have composition of partial objections, isomorphism. And in the right side, we are asking that these maps are equal when we have the product of GH. So we need that this domain is in this domain of alpha GH to this make sense. Then, in other words, we are saying that alpha GH is an extension of this composition, and this domain is bigger than the domain of this composition. And when the ideals are unital, we say that the partial action is a unital partial action. And the definition of Galois theory, the Galois extension is essentially the same, but here we have just one idempotent, which is the identity of the group. And if this G is the identity of the group, in the right side we have 1, otherwise it's 0. So for the rest of this discussion, we are fixing that S is a finite inverse semigroup. And this is the natural partial order associated. And beta is an action of S on the ring A. And we are now defining another trace map. And we will first work with E-unitary inverse semigroups to construct this new trace map. So first, some relevant properties. What is the definition of a unitary inverse semigroup? We say that S is E-unitary if whenever E is in the set of idempotent and E is less or equal than S, then S must be in the set of idempotent, and it works for all S in S. We define the relation sigma on S by S is related to T if and only if there exists an element U that is less or equal than S and T for all S and T in the inverse semigroup. So this is how we define this relation. We will use this notation sigma S for the coset of the element S, and this quotient is in fact a group. These results are classical results. They can be found in the book of Lawson of inverse semigroups. Here these are not original. These are results for Lawson. Casal has this last result. If S is unitary, even only if the coset associated with E is whole the set of idempotents of S. And we use these properties concerning relations and E-unitary inverse semigroups then to construct a partial action of this group. So given an inverse semigroup, we can construct a group. This is the group. And when S is in particular E-unitary, we have that the class of any idempotent is the set of all idempotent. Under these assumptions, we defined a partial action of this group by defining the ideals and the actions, and it is in fact a partial action of the group G on the ring A. And it can be constructed for any inverse semigroup. And here we have the new trace map, which we call sigma trace map. And this new trace map is given by a trace map sigma beta applied on A is simple the trace map alpha applied on A, which means that we are assuming that we're making sums of all elements in this group, the quotient, G are percurring. This is the new trace map. And keeping the same assumptions of the previous theorem, which means we are working with E-unitary inverse semigroups, then we can show that the invariant, the ring of invariants by the action of beta is the same as the invariants by the action alpha. This map is a homomorphism of A beta B modules. This sigma trace map is invariant by beta, and also this equality holds. And that I is beta Galois extension of A beta, even only if A is an alpha Galois extension of A alpha. Then we have a lot of information here because we already have some results concerning Galois theory for partial actions of groups, and then we can translate it to the inverse semigroup context. Another relevant properties is concerning joints, and we say that an element U is a joint Join is the opposite of meet. The join is we said that U is a joint of the elements S and T in the inverse semigroup if S is less or equal than U, T is less or equal than U, and if S is less or equal than V and T is less or equal than V, then U must be less or equal than V. And this is the notation that we use for the join. An inverse semigroup set to be complete if every non-empty compatible subset has a joint, and an inverse subsemigroup T is closed under joins if given a subset compatible such that there exists a joint, then this joint must be in this inverse subsemigroup. So this is what it means closed under joins. This condition here we are presenting because it appears in the Galois correspondence in the new context. So we say that this beta complete if this inverse subsemigroup T is full, and if we have P in T are such that there exists a joint here, and this is associated with determined beta. If this occurs, then this element U, this joint, must to be in T. So it's closed under joins, but concerning the action beta. And when S is in particular a group, every subgroup is beta complete. The partial order here is the equality. And with these informations, I can state the Galois correspondence for E-unitary inverse semigroups. Okay, so summarizing, we defined the new sigma trace map. This sigma trace map, we use the group associated and the partial action of this group to construct this sigma trace map. With this sigma trace map, we can prove several equivalences of the definition of Galois theory. I did not include in my presentation the list of all equivalences of the definition of Galois extension for inverse semigroup, but it is on the paper, but I did not include it here. And we constructed this equivalence using the new trace map. And with this equivalence, then we proved this Galois correspondence. So the sigma trace map, it's fundamental, it's very important to construct this theorem, this correspondence in a more general context. But here we are first working with unitary inverse semigroups. So now, what is this new correspondence? S is a finite inverse semigroup, which is E-unitary, and that acts injectively on a commutative ring. Here, the correspondence here is concerning commutative rings. The first correspondence that I said before, it's also under commutative rings. And the next will also on commutative rings. And suppose that A is a beta Galois extension of A beta, such that each ideal is non-zero. And then there exists a one-to-one correspondence between the A beta separable and beta strong subalgebras B of A and the beta complete inverse subsemigroups T of S. Here we have more subalgebras and more inverse semigroups appearing here than the orthogonal case. Because in the orthogonal case, many ideas were zero, and then in the correspondence there are less structures appearing. And here we are considering all the beta separable and beta strong subalgebras. In the orthogonal case, we are not considering all. They are associated with a maximality. And on the other side, the beta complete is a condition that when we restrict to the orthogonal case, is exactly the same condition that appears there. Okay, so here we are considering E-unitary inverse semigroups, but we are not satisfied. We want to extend to the general case. So how to extend to the general case? The general case, I mean, first of all, inverse semigroups, not necessarily E-unitary, acting on rings, but not necessarily injectively. But here we are considering inverse semigroup without zero at first moment. So we treat these cases separately. Then we proved that assuming that A is a beta Galois extension over A beta and that the ideals are non-zero, then this set is an E-unitary inverse semigroup. Under this assumption, we need that A is Galois over A beta. Then this is an E-unitary inverse semigroup. Furthermore, this inverse semigroup acts on A via this natural action. And if T is an inverse subsemigroup here, then T is beta complete if and only if it is complete. They are the same concepts here in this context. And this is the last concept before the Galois correspondence. A full inverse subsemigroup is said to be beta maximal if, first of all, beta T is complete, and if for each T in T, we have that the preimage of T is in T. But observe that if beta T is equal to T, then this condition is clearly satisfied, and then beta maximal is just complete. And then with these results, we can show that if S is a finite inverse semigroup that acts on a commutative ring A, and assuming that A is beta Galois over A beta, and such that the ideals are non-zero, then there is a one-to-one correspondence between the beta maximal inverse subsemigroups and the separable and beta strong A beta subalgebras. There is a one-to-one. This correspondence is concerning inverse semigroups without zero. And then we have this one-to-one correspondence. When restricting to the E-unitary case, we have exactly the same correspondence because in that context, beta maximal is exactly the beta complete. And finally, in the case of inverse semigroups with zero, we constructed a Galois correspondence for inverse semigroups with zero that is categorical at zero, which means that if STU is equal to zero, it implies that ST is equal to zero or TU is equal to zero. And under this condition, we also have a one-to-one correspondence between the same inverse subsemigroups and the same beta strong separable beta subalgebras of A. The correspondence is exactly the same. And then this is the most general context that we we can work that we worked. I don't know if there's a way to improve this hypothesis, this condition, that maybe for any inverse semigroup with zero, I don't know. Maybe there is a way, but we did not make it. And so these results are found in arXiv. The paper is under peer review. And this is the main references, not all, but the main that we use it here. That in this first reference, it was defined partial groupoid actions concerning globalization, Morita, and something about Galois theory. There's the classical paper by Chase, Harrison, and Rosenberg, which is the first one concerning Galois theory on commutative rings. And some other papers concerning partial actions and the classical book of Lawson. And that is. Okay. Thank you very much for your attention.
Thanks for your talk. Are there any further questions from the audience? Maybe in the chat. I don't see. I have a little further question. At a certain point, actually two questions. At a certain point, you had a condition about what's the opposite of meat? The supremum. I don't know how you call it. Before, there was some condition on a union that, there. Yeah.
Here.
Yeah, so this reminded me vaguely, but I'm not sure, about, about Excel's condition of tightness for a semigroup action. Rui Excel, this semigroup person. Well, who is in Florianopolis. So there's a notion of, that essentially says that, if you have that the union goes to the supremum whenever this is defined. But I thought it reminded me a bit of that. And then the more philosophical question maybe is that the way you jump from the so you go from the partial group actions to the E-unitary semigroup actions because some local group partial group actions appear in the E-semigroup case. And then,
I went for the E-unitary case because we need that this action should be a partial action.
yeah. Okay. So with E-unitary groupoid actions, you reduce somehow to partial group actions, and then
Yes.
in the general case, you reduce to E-unitary group actions because E-unitary group actions do appear in nature even if the groupoid is general. That's the semigroup is general. That's essentially the idea, if I understood correctly, right?
Right.
Okay.
Okay,
So the unitarity condition seems to be very closely related to the Galois condition. because this automatically, this is what the proposition says, right? That
Right.
you impose Galois and then a E-unitary inverse semigroup shows up. Yeah. So I wonder, yeah. Oh. So maybe, yeah, okay. This is very interesting. In the, in this world of the Hopf algebraists, they also have Galois extensions. Yeah, Galois, but it refers to an action of the Hopf algebra, which I think semigroup algebras are not such algebras. But I don't know if there is any relation with that. So in the case of when the Hopf algebra is a group algebra, you get the usual definition of Galois extensions. But then you can consider other Hopf algebras such as universal enveloping algebras and Lie algebras, and then you get something different. I don't know if
there is a paper of Eliezer, Marcelo, and I don't remember the third author. It's very recent, and they defined quantum inverse semigroups. Do you know this paper?
I know Eliezer, but I don't know the paper. Yeah.
And they defined in a Hopf context, and it's an algebraic structure that generalizes algebras of inverse semigroups in a Hopf context. But it also works for algebras of inverse semigroupoids as well, or inverse categories. But I don't have any idea how can be a Galois extension in that context. But I assume that must be very similar to the Hopf context because we have group for Hopf, then groupoid for weak Hopf. And I believe that there should be something very similar that inverse semigroups to quantum inverse semigroup. But I did not investigate. I'm assuming that should be a very close definition to this case also.
Yeah, I remember some years ago, I wrote a paper that involves the algebra of, so you consider I of the natural numbers, right? So the partially defined bijections between subsets of the natural numbers. And then you take the semigroup algebra of that inverse semigroup, and you mod out by the relation that the characteristic function of two disjoint subsets is the sum, right? So this is the condition of tightness in the sense of Excel. And then I wanted this to find a definition of a Hopf algebra, weak Hopf algebra, or whatever that this would satisfy, and I couldn't find any. So, I mean, yeah. So maybe this fits this setting that you just mentioned of the user. Yeah. Well, anyhow, thank you very much for your very interesting talk. And I hope you find you are interested in our seminar and maybe join us for a talk that interests you in the future.
Absolutely. Thank you very much.
Okay. Goodbye. Thank you.
Goodbye. Thank you.
Bye.